सब समझ आ रहा है, कोई प्रॉब्लम्स कहीं नहीं हो रही हैं. इज दैट ट्रू? कोई प्रॉब्लम्स कहीं नहीं है? Okay, if there are no doubts, let's start with the review. Um, okay. Who would like to point out कि हमने पिछली क्लास में क्या क्या किया था? तिशा, any ideas? पिछली क्लास में हमने क्या क्या किया था? आप लोग को मेरी आवाज आ रही है?
Yes, sir. So we started from Avogadro's law.
We started with the Avogadro's law. Okay,
When
we did Avogadro's law. What was Avogadro's law? किसी को याद है?
equal volume of all gases under similar condition of
I'm
temperature.
sorry, I'm sorry, I'm sorry. Can you repeat that? आपकी आवाज नहीं आ रही. Could you repeat that?
Yes, yes, yes. Now I'm audible.
Yes, yes, you're audible, audible.
Equal volume of all gases at similar at this
Yes.
same conditions, temperature and pressure have equal number of moles.
Yes, if you have the same pressure, volume, and temperature of two gases, then the number of molecules would also be exactly the same. How do we know that? We know that because PV is equal to NKT, right? Or PV is equal to nRT. If P, V, and T are the same, then N has to be the same. That is what Avogadro's law says, and we also went ahead and proved it by taking a toy model, and the toy model that we were talking about was the ideal gas, right? उसके हमने so initially we started with pressure, volume, and temperature, and actually defining कि what this pressure, volume, and temperature are in terms of आपकी जो microscopic quantities हैं, जैसे आपकी velocities and positions. So we took these two and we showed how we can derive pressure from these basic quantities and temperature from these basic quantities, right? Well, very good. We were able to do that. Then we showed that this formalism that we built also predicted other things like Avogadro's law, things like Dalton's law, and Dalton's law of equal pressure, and we realized that this model that we are building is is at least good enough to go ahead and try to figure out more things about this model. So one very obvious thing that comes to mind is that yes, we understand how velocities change into pressure and temperature, right? But what happens to the energy in this microscopic view of the world, where gases are made of these molecules? Where is the energy actually stored? And the answer comes from a very surprising place. Actually, not a very surprising place, but you'll understand why it is surprising as we go ahead. The answer comes in the form of the degrees of freedom. Degrees of freedom. There's no apostrophe here. What do you mean by a degree of freedom? It essentially is just counting the number of actual variables there are. That is it. It's just counting the number of variables. For example, you have a molecule kept here. How many degrees of freedom does it have? Well, it has a degree of freedom along the x-axis. It can move along the x-axis. It can move along the y-axis. That's two, and it can also move along the z-axis, right? X, y, and z. This particle can move anywhere in these three directions. So for a single particle, what is the degree of freedom? It's just three. So your degree of freedom is just 3. Now think about a slightly different thing. Think about something that has two molecules and it's connected by a bond. And the bond is hard enough so that it does not act like a spring. So आप इसको एक stick की तरह imagine कर सकते हो. In this case, what should be the degrees of freedom?
Excuse me, sir.
Yes, go ahead.
Sir, I just came, so could you please tell me what all we have discussed?
Right now, we're just discussing about how energies. So we already figured out from the previous classes how velocities give us pressure and temperature, right? Now the question is how energies are essentially how does this microscopic view of the world, this kinetic view of the world, how does this essentially store the energy? That is the question. And the answer to where these energies are stored is in what we call as the degree of freedom. We can formally define the degree of freedom as degrees of freedom as following. Um, the degrees of freedom of a dynamical system. Dynamical system. Let's erase all of this. When one says a dynamical system, one is talking about either molecule, a diatomic molecule, a triatomic molecule, or any kind of system one can actually imagine. Even hard bodies one can think of, and we will think about all these things. Let me systematically define this first. The degrees of freedom of a dynamical system are defined as dynamical system are defined as uh, the total number of the total number of coordinates. You can think of these as coordinates, right? So these are essentially the directions in which you can move. So those are essentially the coordinates, or so coordinates underlined, independent or independent quantities. Independent quantities is important. Um, Independent quantities required to describe completely the position and configuration um, configuration of the system. Okay. So this is how you define degrees of freedom. It is essentially, so you can define it for a dynamical system. Essentially, a system which moves is defined as the total number of coordinates or independent quantities. So coordinates. In the case of a monatomic gas, you can move in the x direction, y direction, z direction. So total number 3. So hence the degrees of freedom is 3. Now, what about this case? What are the degrees of freedom of this diatomic molecule, which is essentially held together by a let's say a stick.
One.
1 degree of freedom. Why?
It can either go towards the negative x-axis or the positive x-axis.
So see, first of all the system can go towards the left or the right, so along the x-axis, so that is one, but it can also go along the y-axis, right?
So is it about a single atom or the whole molecule?
The molecule.
Yeah.
The molecule can go, पूरा molecule x direction में जा सकता है, y direction में जा सकता है और z direction में जा सकता है, right? So वहां से 3 हो गए, एक दो तीन, यहाँ वहां से 3 हो गए. But the diatomic molecule can rotate also, right? So the diatomic molecule, it can rotate about this axis, or it can rotate about this axis. it Rotating about the third axis, which is essentially, if this is a diatomic molecule, rotating about this axis does not really makes any sense, right? Because it's just a straight line. So rotating does not change anything. If it's rotating like this, it is changing the configuration. If it's rotating like this, it's again changing the configuration. But if it's rotating like this, it's not changing the configuration. So there are two of those. So essentially there are 3 plus 2, 3 from translation and 2 from rotation. So hence total number of degrees of freedom, f, let's call them f, is equal to 5. Correct?
Yes, sir.
Now let's say if you have a 3, if you have 3 molecules which are essentially, which we have 3 atoms making a molecule which is essentially the ends of a right angle, of an equilateral triangle. What are the degrees of freedom here?
6.
6. Why?
Because 5 from the last one, and one is that the rotation you said that will not be applicable for 2.
Yes, also all 3 rotations and all 3 translations. So 3 translations, which essentially means कि तुम x एक्सिस के अलावा पूरा ये ट्रायंगल लेके यूं शिफ्ट कर सकते हो, ऊपर नीचे शिफ्ट कर सकते हो, आगे पीछे शिफ्ट कर सकते हो, ये हो गए 3. या फिर तुम इस एक्सिस के अराउंड रोटेट कर सकते हो ऐसे करके, इस एक्सिस के अराउंड रोटेट कर सकते हो ऐसे करके, या फिर तुम इस तीसरे एक्सिस के जो अंदर बीच में से जा रहा है, अगर ये एक ट्रायंगल है उसके बीच में से एक्सिस जा रहा है, उसके अबाउट भी तुम ऐसे करके उसको रोटेट कर सकते हो, राइट? So these are the 3 degrees of freedom because of rotation. So total number of degrees of freedom is 6. One can make a general rule out of this. So let's say if there are, let's say there are n such atoms inside one molecule, and there are k connections. Okay, and there are k connections. So what is the total degrees of freedom that one can figure out from here? If there are, yeah, so essentially it will be, for every single atom, you can think of it like all 3 atoms initially, let's say n is equal to 3, all 3 atoms initially could move in all directions. So हर एक atom का 3 3 था, right? So ये वाला atom जो है ये 3 direction में जा सकता था, ये वाला atom भी 3 direction में जा सकता था, ये वाला atom भी 3 direction में जा सकता था. Total क्या है? 3 times 3. But now they're constrained. How many constraints there are? There are 3 constraints. So you subtract the 3 from that. And what you get is 9 minus 3, which is 6. This is essentially what we got in the case of a um, in the case of a triatomic molecule. Similarly, if you look at in the same way you look at a diatomic molecule, what you are seeing is that you have 2 singular atoms which can move in 3 directions each. So there are 3 into 2 because of the 2 atoms and 3 directions that each of them can move, and one constraint. There is only one constraint, so -1. So that's 6 minus 1, that's 5. And that is exactly what we got in the last case. So one can also essentially not only just think of it like, think of it like how many ways it can move. One can also think of it in a way that all of these individual parts can move, but then after that you're putting in additional constraints. Okay, so the total number of degrees of freedom should be 3n minus 3. Correct? Yes,
Yes,
no,
sir.
yes. Where n is the number of particles, जो भी आपके number of atoms in the molecule. Lovely. So this is essentially the total number of degrees of freedom. So now till now we've only talked about molecules which are
And
held
so, how
together.
do we determine the constraints?
The constant, what constant?
How do we determine them?
How do you determine what?
I mean, there's a formula for this F is for the ways how it can revolve or sorry translate or rotate in a space. But
Uh,
what for K?
K is essentially the number of constraints, right?
No, no, no,
So,
sir. Sir, it's
huh?
like one molecule के लिए there are no constraint. For
Yes.
two there is one, three के लिए three. So if there n, how will we determine the constraints?
See, actually, to be honest, there can be any number of constraints. For example, your molecule, let's say you have a four atom molecule. It can be connected like this, or it can be connected like this, right? Here, in this case, you have four constraints, and in this case, you have six constraints. So, in the same number, you can have different kinds of constraints as well. So, number of constraints depend on the shape of the molecule itself. So for example, if you have water, H2O, you have oxygen on top and you have connecting a hydrogen here. But you have CO2, which is a carbon in the center and with a double bond, you have oxygen here. So the shapes are very different. So for this kind of a case, try to calculate this is what is called a non-linear, um, non-linear molecule. For a non-linear molecule, हमने already calculate कर लिया है कि there are six such constraints. But what if it's not a molecule like this? What if it's molecule just like this? So what are the degrees of freedom of such a molecule?
Two.
How many degrees of freedom?
Sorry, constants are two. We'll have it
There's 7.
six.
Yes. So 3, n is 3 minus k is 2, one from here, minus 2. That's what? 9 minus 2, which is 7. So you have degrees of freedom. Calculate for a linear molecule कितना होना चाहिए? For a linear molecule, you will understand why this is important in just a minute.
Linear molecule.
Sir,
How
5.
5. Why 5?
sir will it not be seven?
Yes, it will be 7. Why would it be 7? Because again, it's the same thing as here. It didn't matter. Why did it not matter? It did not matter because the number of constraints are the same and the number of molecules are the same. Number of atoms are also the same. So you have 3 into the number of atoms minus 2, which is again 7. Lovely. Now, let's अभी तक हमने जो लिया है were essentially two atoms which are connected by a stick. But now what you do is you increase the temperature. You increase the temperature such that ये hard नहीं रहते, ये vibrate करने लगते हैं. In the sense, at higher temperature, this happens at T low, at T high. What happens is that this becomes like a spring. Now it can vibrate also. So now in this case, when it can vibrate, in at the case of high temperature, during the case of high temperature, what happens for a monoatomic gas? So you have only one atom. How many degrees of freedom?
Three.
Again
3.
3, because nothing is changing. But what about a diatomic gas?
6.
6. That's lovely. Now, why 6?
Plus one for this vibration.
Yes. So essentially, 5 degrees of freedom is equal to 5 from the case where it was hard. The stick was essentially hard, plus 1 because of vibration. But notice one very interesting thing. Notice a very, very major difference here. All these 5, ये 5 कौन से थे? These 5 were translation of, so you have a diatomic molecule here, let's say you have a diatomic molecule kept here. This is point A, this is point E, B. सो तीन जो थे वो ट्रांसलेशन से थे, यानी कि ए बी को यहां से पकड़ा, उसको एक्स एक्सिस में हिलाया, वाई एक्सिस में हिलाया, या फिर आगे पीछे जेड एक्सिस में। उसके अलावा इसको यू रोटेट किया या फिर यू रोटेट किया, ये पांच थे। व्हाट डज वाइब्रेशन डू? वाइब्रेशन, ये जो पांचों हैं, these only have kinetic terms, right? इन द सेंस कि इनकी जो एनर्जीज हैं वो खाली काइनेटिक एनर्जी है। ट्रांसलेशन इज जस्ट काइनेटिक एनर्जी, रोटेशन इज जस्ट रोटेशनल काइनेटिक एनर्जी, देयर इज नो पोटेंशियल एनर्जी हियर, राइट? But in the case of a vibration, when two atoms are held together, they are moving apart also. So it has both kinetic energy because the atoms themselves are moving, and potential energy because there is a spring. So in the case of vibration, there is kinetic energy plus potential energy. This becomes very important. This becomes very important, and very soon it becomes important. Let's just continue this pattern. इसको triatomic non-linear gas के लिए बताओ।
सर एक
non
क्वेश्चन।
हाँ,
सर ये मोनोटोमिक के लिए तो ऐसे 4 होना चाहिए था, बिकॉज वो भी तो वाइब्रेट करेगा, तो एंड वी नॉट कंसीडरिंग वाइब्रेशन एज अ पार्ट ऑफ ट्रांसलेशन।
no, wait. मोनोटॉमिक गैस में खाली एक ही एटम है,
यस सर।
देर इज नो स्प्रिंग अटैच टू इट, तो वो वाइब्रेट अगर कर भी रहा है, इट इज एसेंशियली ट्रांसलेशन, राइट? इन द डायटोमिक गैस, व्हेन आई एम टॉकिंग अबाउट ट्रांसलेशन, आई एम सेइंग कि दोनों को मैंने फिक्स कर रखा है और दोनों को साथ में हिला रहा हूं मैं, ये आगे पीछे नहीं जा रहे हैं, ये दोनों को हिला रहा हूं, वाइब्रेशन की वजह से ये आगे पीछे जा रहे हैं। अंडरस्टैंड द डिफरेंस?
यस सर, मतलब मोनोटोमिक के लिए वो ट्रांसलेशन खिलाएगा और इसके लिए वाइब्रेशन।
बट वाई बिकॉज मोनोटॉमिक में तो खाली एक ही है, राइट? वो यूं हिले कोई फर्क नहीं पड़ता। देयर इज नो वाइब्रेशन, वाइब्रेशन इज एसेंशियली ट्रांसलेशन। व्हेन इट्स डायटोमिक गैस, जब तुम वाइब्रेट कर रहे हो, तुम उसको ट्रांसलेशन की तरह नहीं लिख सकते, क्योंकि ये जो स्टेट है, फॉर एग्जाम्पल यहाँ पे मैं बना रहा हूँ, ये जो स्टेट है और ये जो स्टेट है कि ये एक्सपैंड कर गया, एक उसमें एक स्नैप एक फोटो लिया मैंने इस पॉइंट पे, इस टाइम पे, और एक फोटो लिया मैंने इस टाइम पे, क्या किसी भी ट्रांसलेशन करके तुम इस पे पहुंच सकते हो? नहीं पहुंच सकते, राइट? बिकॉज ट्रांसलेशन में ये जो लेंथ है ये कांस्टेंट रहती है। इसको मैं ऐसे ही उठा के आगे पीछे कर रहा हूँ, ऊपर नीचे ला रहा हूँ, और आगे पीछे ला रहा हूँ। बट दिस सेपरेशन, दिस इज अ डिफरेंट काइंड ऑफ, दिस इज अनदर काइनेटिक एनर्जी, कि अब तुम सेपरेट भी हो सकते हो। दिस इज एन एडिशनल काइनेटिक एनर्जी, राइट?
यस सर, गॉट इट सर।
यस, सो दिस इज स्लाइट डिफरेंस दोनों में, और ये बहुत इंपॉर्टेंट है ये डिफरेंस करना, क्योंकि अगर ये आपकी चीजें क्लियर हैं तो आपकी बहुत सारी चीजें ऑटोमेटिकली क्लियर हो जाएंगी। व्हाई? बिकॉज ऑफ द लॉ, एक्चुअली नहीं, वही लॉ पे नहीं याद है अभी मेरे को। नॉन लीनियर बताओ कि इसमें क्या है? नॉन लीनियर
सर
गैस
9।
इक्विलेटरल ट्रायंगल। हाँ, एट हाई टेम्परेचर्स इसकी क्या डिग्रीज ऑफ फ्रीडम होगा? यानी कि यहाँ पे मैंने स्प्रिंग लगा दी है,
8.
वाई 8?
सर 9।
9? 6 बिकॉज 6 पहले से थे। 6 कौन कौन से थे? तीनों ट्रायंगल, एक ट्रायंगल है, इट कैन मूव इन अलोंग द एक्स एक्सिस, इट कैन मूव अलोंग द वाई एक्सिस, इट कैन मूव अलोंग द जेड एक्सिस, it can rotate about like this, it can rotate like this, it can rotate, what's the third axis? Like this, right? It can rotate 3 times and it can translate 3 times. Notice again, all of these kinetic, plus 3 of them can vibrate. So because of this springs जो आ गए, +3 हो जाएगा, so that makes it 9. Notice what is happening. This is essentially going, what this spring is doing is essentially adding another k. So जो हमारे डिग्रीज ऑफ फ्रीडम में हमने 3n माइनस k किया था जब वो स्टिक्स थे, हम इसमें बस एक प्लस k कर रहे हैं बिकॉज हर उस स्टिक को हमने स्प्रिंग बना दिया। सो डिग्रीज ऑफ फ्रीडम एट हाई टेम्परेचर हमेशा 3n होगा। सो फॉर अ ट्रायटोमिक गैस, कोई कैसी भी ट्रायटोमिक गैस हो, उसका हाई टेम्परेचर पे जो डिग्रीज ऑफ फ्रीडम होंगी वो 3n होंगी। मेक सेंस?
सर लेकिन ये कांस्टेंट आया कहाँ से?
कौन सा कांस्टेंट?
ये प्लस के जो आपने किया है इसमें।
ये प्लस की ये जो हमारे बॉन्ड्स थे, उनको अब मैंने स्प्रिंग बना दिया ना। जो पहले ये कंस्ट्रेंट ला रहे थे, अब मैंने उनको कंस्ट्रेंट नहीं छोड़ा है, उनको मैंने स्प्रिंग बना दिया।
सर बट ये थोड़ा कहना थोड़ा क्या कहते हैं गलत नहीं होगा सर, बिकॉज वो एक्चुअली कांस्टेंट है नहीं, वो उसे और फ्लेक्सिबिलिटी दे रहा है टू वाइब्रेट एंड गेट अपार्ट।
No, it is adding the degrees of freedom. That is what it is doing. It is adding the number of ways it can move around. F जो है हम डिग्रीज ऑफ फ्रीडम कैलकुलेट कर रहे हैं ना। ये जो पहले आप जब हार्ड थे उसके बॉन्ड्स, जब स्प्रिंग नहीं था, तब ये कंस्ट्रेंट कर रहा था आपको, ये आपको इससे दूर जाने नहीं दे रहा था, वो आपको यहीं पे फिक्स
या
करके
सर
रखा
सर
था।
दैट इज व्हाट आई सेड कि मतलब वो उसे और फ्लेक्सिबिलिटी प्रोवाइड कर रहा है, बट स्टिल वी आर एडिंग प्लस के।
यस, बिकॉज व्हाट आई एम डूइंग इज कि मैं एक को छोड़ के बाकी सबको स्प्रिंग नहीं बना रहा हूँ। जब मैं टेम्परेचर राइज कर रहा हूँ, मैं सबको स्प्रिंग बना रहा हूँ। और एक बार जब वो स्प्रिंग बन गए, जो माइनस किया था वो मेरे को हटाना पड़ेगा अब, है ना।
ओके ओके ओके, वो अच्छा
तो
सीन है।
इसलिए वो वापस 3 के हो जाएगा।
ओके ओके सर, गॉट इट सर।
मेक सेंस? बट द
एक्चुअली
इंपॉर्टेंट थिंग इज दैट
सीम
दिस
लाइक कि आप
वाइब्रेशन, हाँ,
इट सीम लाइक दैट यू आर एडिंग अ कांस्टेंट बिकॉज यू रोट प्लस के।
yes, so I mean I'm adding the constant from the case where it was initially a minus k.
यस सर,
So
गॉट इट
yes,
सर।
yes, so I mean yes, you're right, you're not wrong. Anywho, yes, but the important thing here is that vibration, the vibration mode, जिसको हम vibration mode कहेंगे, कि यहाँ पे this vibration mode has both kinetic and potential part to it, so it is double. This is kinetic and potential. Now, where does this become important? This becomes important when we're talking about the law of equipartition of energy. What does this law say? This law says कि जितने हमारे डिग्रीज ऑफ फ्रीडम है, हर एक डिग्री ऑफ फ्रीडम में एक फिक्स अमाउंट ऑफ एनर्जी जा सकती है, डिपेंडिंग ऑन द टेम्परेचर. व्हाट इज दैट फिक्स अमाउंट ऑफ एनर्जी? दैट इज हाफ केबी टी. हर एक डिग्री ऑफ फ्रीडम में हाफ के बी टी एनर्जी जाएगी. दिस विल बी ट्रू फॉर बोथ आर काइनेटिक केसेस एंड पोटेंशियल एनर्जी केसेस. इसका क्या मतलब हुआ? ये थोड़ा कंफ्यूजिंग हो गया. इसका क्या मतलब हुआ? इसका मतलब ये हुआ कि जो रोटेशन और ट्रांसलेशन वाले जो डिग्रीज ऑफ फ्रीडम है, उन उन हर डिग्रीज, लेट्स से वो F1 है, ठीक है. F1 जो है वो रोटेशन और ट्रांसलेशन को मिला के, इन सब में हाफ केबी टी एनर्जी स्टोर होगी. और जो वाइब्रेशन वाले मोड्स हैं, लेट्स कॉल देम F2 मोड्स, दीज वाइब्रेशन मोड्स, सिंस उसमें काइनेटिक एनर्जी में भी एनर्जी जा रही है और पोटेंशियल एनर्जी में भी एनर्जी जा रही है, सो इट विल डबल ऑफ दैट. सो इट विल बी हाफ केबी टी. दिस इज फॉर द काइनेटिक केस, काइनेटिक एनर्जी केस, प्लस हाफ केबी टी फॉर द पोटेंशियल एनर्जी. सो दिस इज एक्चुअली केबी टी. सो हर एक ट्रांसलेशन और रोटेशन डिग्रीज ऑफ फ्रीडम में हाफ केबीटी एनर्जी स्टोर्ड होगी, और हर एक वाइब्रेशन मोड में केबीटी एनर्जी स्टोर्ड होगी. दिस इज व्हाट द लॉ ऑफ इक्विपार्टीशन ऑफ एनर्जी सेज. डज दैट मेक सेंस?
यस सर।
लवली. इसका मैं बाकायदा स्टेटमेंट, जो एक्चुअली उसको जो अगर एग्जाम में आता है कि व्हाट इज
Sir, so can we calculate the number of molecules in a system if we have provided the energy already by this formula?
yes, exactly, and that is exactly what we are going to do ahead next. But let me before that write all of these things down. मतलब इसको सिस्टमैटिकल वे में इसका डेफिनेशन लिख दूं, ताकि अगर एग्जाम में कोई पूछता है आपसे, तो फिर आपको पता होना चाहिए लिखना क्या है. Law of equipartition of energy. It states that it states that uh, in any dynamical system, in any dynamical system which is in thermal equilibrium, which is in thermal equilibrium is important. Thermal equilibrium, underline thermal equilibrium because it's important, which is in thermal equilibrium, um, comma, the energy is equally distributed amongst its various degrees of freedom, and the energy associated associated with each degree of freedom, with each degree of freedom per molecule is half kBt. Per molecule is also important. Is half kBt, where kb is Boltzmann constant and T, where kb is Boltzmann constant and T is just the temperature. Okay, write this down, please. Do you want to know how do you prove this? It's very easy.
Yes, sir.
Okay, it's very easy. Go back to your description. And what was the average kinetic energy that we got? It was 3 by 2 kT, right? याद है पिछली क्लास में किया था या उससे पिछली क्लास में when we took out the average of kinetic energy, and actually when we were defining temperature, we got it in terms of V and then we got it in terms of kinetic energy, right? V square का average के terms में, और kinetic energy हमने 3 by 2 kBt आया था हमारा. Kinetic energy क्या होती है? Kinetic energy is just half m times average V squared, correct?
Yes, sir.
And this average V squared is nothing but average Vx squared plus average Vy squared plus average Vz squared, right? एंड हमको ये भी पता है कि एवरेज Vx squared जो है that is equal to average Vy squared, which is equal to average Vz squared. So what happens? So this average V, which is just the sum of the average Vx and Vy and Vz. Um, yes. So what does this make? This makes that, okay, let's just put in the values. What do you get? You get V squared, right? So you get 3 Vx squared is equal to 3 by 2 kBt. Correct? Yes, no, maybe. ये एवरेज वी की वैल्यू उठा के यहाँ से डाली है. सो आई हैव रिटन दिस एज वी एक्स स्क्वायर्ड का एवरेज प्लस वी वाई स्क्वायर्ड का एवरेज प्लस वी जेड स्क्वायर का एवरेज. And we've used this second equation to say that this is equal to this is equal to this. इसको vx बोल दिया, इसको vy बोल दिया, इसको vx बोल दिया, इसको भी vx बोल दिया. So that's why this is 3vx and there is a half m also. Um, yes, half m, sorry. 3 times half m. So, which is essentially, so half m vx square, which is also equal to half m vy square, which is also equal to half m vz square, is just the kinetic energy in the x direction, or the kinetic energy in the y direction, or the kinetic energy in the z direction, right? And what is that equal to? So kinetic energy in the x direction is just equal to half kBt, and hence proved, because this has to be equal to half kinetic energy, average of kinetic energy in the y direction, which has to be equal to average of kinetic energy in the z direction. So this is the proof for the kinetic energy part. For the vibration part, it's slightly more tricky, and it's not in your syllabus, so we don't really have to go about doing that.
सर इससे एक और चीज कंक्लूड कर सकते हैं ना कि वी कैन नॉट टेक द एवरेज फॉर दिस फॉर्मूला वी कैन नॉट टेक काइनेटिक एनर्जी एवरेज फॉर ऑल थ्री डायमेंशंस बिकॉज हमने
See, the kinetic energy average for all three dimensions has to be the same. That is because Vx square ka average is equal to Vy square ka average is equal to Vz square ka average, right?
और सर जो हमने इससे पहले किया दैट इज दिस विदाउट एनी दिस सबस्क्रिप्ट वी स्क्वायर वो क्या था
That is essentially Vx plus Vy plus Vz, no? ये लिखा तो है यहाँ पे.
सर सर वही तो मैं कह रहा हूँ कि मतलब हम तीनों का एवरेज एक साथ नहीं बता सकते ना
बता सकते हैं, that's the point. Because Vx square is equal to Vy square is equal to Vz square. Hence, you can show that the kinetic energy in the x axis is half kBt. You can show that. Make sense? सो हर उसमें हर डिग्री ऑफ फ्रीडम में हाफ के बीटी होगा अगर वो काइनेटिक है. दैट इज व्हाट दिस शोज. एंड फॉर पोटेंशियल, बिकॉज देयर आर टू पार्ट्स, काइनेटिक एनर्जी एंड पोटेंशियल एनर्जी, सो इट विल बी हाफ के बीटी प्लस हाफ के बीटी, विच इज के बीटी. Lovely. Once this is clear, we can go ahead and
Sir,
actually.
sir,
Huh?
previous slide थोड़ा दिखा दीजिए.
I'm sorry.
Sir, go back to the previous slide.
Previous slide. Okay. Tell me when you're done.
Done, sir.
Lovely. Okay, lovely. Okay, so once we know now, okay, so now what do we know? We know कि individually आप हर मॉलिक्यूल को कुछ डिग्री ऑफ फ्रीडम असाइन कर सकते हो. हर मॉलिक्यूल की कुछ ना कुछ डिग्री ऑफ फ्रीडम होगी. एंड आपने उसके बाद हमने लॉ ऑफ इक्विपार्टीशन ऑफ एनर्जी ने ये बताया कि हर उस डिग्री ऑफ फ्रीडम में कितनी एनर्जी स्टोर होगी, राइट? नाउ अगर हमको ये पता चल गया कि कितनी एनर्जी स्टोर हो रही है, तो यानी कि हम उसकी स्पेसिफिक हीट निकाल सकते हैं. बिकॉज व्हाट इज स्पेसिफिक हीट? स्पेसिफिक हीट इज टॉकिंग अबाउट कि कितनी एनर्जी स्टोर हो सकती है, राइट? स्पेसिफिक हीट इज कि एक डिग्री बढ़ाने के लिए आपको कितनी हीट स्टोर करनी पड़ेगी, राइट?
यस सर
एंड वो हीट कहाँ स्टोर हो रही है? वो इन्हीं मोड्स में स्टोर हो रही है. So from here you can actually go ahead and actually calculate the specific heats of a lot of things, and we're going to do that. Specific heat. First case, let's think about the specific heat of a monoatomic gas. Now, I will do this one for the monatomic gas. Degrees of freedom, 3. So total energy, uh, so average energy, um, what have I written? Average energy is what? 3 by 2 kBt, because 3 translations हैं. There is no rotation. जब एक point क्या rotate करेगा? That cannot rotate. So that's 3 by 2 kBt. Lovely. Okay. Now how many? That's the average energy of each molecule. Each atom in this monoatomic gas. Molecule is the same as atom because it's a monoatomic gas. Okay. So what's the total energy? Let's say of 1 mole of such a gas. Well, that's just 3 by 2 kBt, जो एक का था, multiplied by multiplied by the total number of molecules. So if you're talking about 1 mole, so that's just Avogadro's number. right? And this is just equal to 3 by 2 kb multiplied by na multiplied by t. And kb multiplied by na in the last class we figured out is just r, right? It's just the gas constant.
Yes, sir.
So this is nothing but 3 by 2 RT. So एक mole of a monatomic gas will have the total energy will be the total internal energy that can be stored will be 3 by 2 RT. So what is CV? So this is essentially the storage wala, right? This is storage. So this is nothing but internal energy. So this is U. So what is CV? CV is just du by d by dt, which is nothing but 3 by 2 r t ka d by dt, d by d capital T, sorry, 3 by 2 है यहाँ पे. 3 by 2 r is a constant, it will just fly out, and d by dt of t is just 1. So this is just 3 by 2 r. So yeah, so starting from the fundamental, from literally the law of equipartition of energy, we can actually show that the specific heat at constant volume for a monatomic gas will always be 3 by 2 or 1.5 times R. Make sense? So from here you can calculate Cp also. What is Cp? Cp is R plus Cv. So this is just equal to 5 by 2 times R. And hence what's gamma? Cp by Cv, which is 3 by Cp by Cv, sorry. So 5 by 2 r, 5 by 2 r divided by 3 by 2 r cancel and 2 to cancel. So this is just 5 divided by 3. So essentially, for a monatomic gas, just by realizing this basic phenomena of you can figure out what this specific heat. You don't have to really go out and do an experiment. You can actually just theoretically predict what the specific heat or the constant, the gamma constant, adiabatic constant of the gas will be. Isn't that amazing? Now, let's do that for the next case. Let's do that for the diatomic case. Diatomic case, first case will obviously be cold. So cold का क्या मतलब है कि it's not a spring yet.
Constant, sir.
Yes, it's a distance. So I would like you guys to go ahead and tell me CV क्या आएगा. इसका CV क्या आएगा, P क्या आएगा और गामा क्या आएगा. अभी जो एक्सरसाइज की है एग्जैक्टली वही एक्सरसाइज करनी है. If you guys understand this, you most of thermodynamics should be clear. हाँ,
For cold or this, अभी cold क्या निकालना सर?
लिखा कोल्ड है ना.
Yes, yes.
Come on, it should not take that long. It should not take that long. 5 मिनट 2 मिनट में आना चाहिए. Literally like this. इतना टाइम नहीं लगना चाहिए. If you understand the basic concepts. Wait for 20 more seconds. 2.5 R, 5 by 2. Lovely. 7 by 2, yes. And yes. Lovely, lovely, lovely. So lovely. So I think some of you have gotten the answer. So, okay, let's think about this. What is the number of degrees of freedom in this case? Well, the total N is 2 and total number of constraints k is 1. So it's 3n minus k, so which is 3 multiplied by 2, which is 6 minus 1, which is 5, right? So this is 5 total modes that where the energy can go. Notice that all these 5 nodes are just kinetic in nature. So यानी कि सब में energy कितनी जाएगी? So what will be u? It will just be 5 by 2 RT, because it was 1 by 2 for everyone, for each. So 5 by 2 kT for one molecule, and for any number of molecules it will be 5 by 2 RT. Once you have this, you can calculate CV by using du by dt at constant v. इसमें v का कोई dependence है नहीं, so lovely. So what is this? This is just 5 by 2 r. You got CV. CP is R plus 5 by 2R, which is 7 by 2R. And gamma is CP divided by CV, which is 7 by 5. Make sense? सब कुछ समझ आया?
Yes, sir.
Lovely. Now, what about the hot case? We are again in the diatomic molecule, diatomic gas case, but this time it's hot. What happens? Calculate CP, CV, and gamma. यार देखते ही बता देना चाहिए तो 3r 4r 4 by 3. हाँ, why 3? Wait, I think I know what you're doing. Think about it for a second. 3r जो आपने 3 जो लिखा है, this is essentially coming from the fact that there were 9 total degrees of freedom, right? But remember, 6 of those are translations and 3 of those are vibrations. So vibrations में एक एक एनर्जी में हाफ के बीटी काइनेटिक और पोटेंशियल की वजह जाएगा, तो टोटल हर एक उसमें हर वाइब्रेशन मोड में केबीटी एनर्जी जाएगी. So it will be more than that. I'll do this. Just tell me the answers quickly. 7 by 2. Nice. Good. Okay, let me go ahead and do this quickly because इसके आगे ट्राइटोमी भी करना है, फिर और भी चीजें करनी है, तो इसलिए इतना टाइम नहीं है. So what is this diatomic molecule look like? You have two molecules connected by a spring, right? Lovely. So degrees of freedom, total number of degrees of freedom. Degrees of freedom will be degrees of freedom in the strict case, in the cold case. Let's call it the cold case, or the solid, not the spring case or the solid stick case, plus the number plus k, right? So this is essentially, um, 3 times 2 minus 1 plus 1. So this is 3 times 2. So this is just 6. Now there are 6 degrees of freedom, correct? But one has to realize that out of these 6, 5 are because of three, there are 5 because of only kinetic energy, in the sense that there are 3 which are because of translation. ये पूरा यूं जाएगा, ऊपर नीचे जाएगा, आगे पीछे जाएगा. 2 because of rotation, ये यूं घूमेगा या फिर यूं घूमेगा. तीसरा क्यों नहीं हो सकता? तीसरा इसलिए नहीं हो सकता because there is no point in rotating about this axis, right? Because it's one dimensional. तो there is is no change when you rotate around this axis. So hence five, all of these three and two, all of these five are kinetic, and the remaining one, that is vibration. So what's the total energy? Well, the total energy is number of kinetic, which is 5 multiplied by half kBt, plus number of vibration, which is kBt. So this is 7 by 2 kBt. Lovely. So this is U. So what is CV? That is du by dt at constant V, which is what? Which is what? 7 by 2 R. In this case, R कैसे है आप for one molecule? This is just for one molecule. Now we're calculating for 1 mole. So that's why 3 by 2 R. What about CP? Well, CP is R plus CV. So this is the 7 by 2 plus 1, which is 9 by 2 R. And gamma is CP divided by CV, which is 9R by 2 divided by 7R by 2. 2R and cancelled out. So this is just 9 by 7. Make sense?
यस सर. सर
Lovely.
ये वाइब्रेशन का पोटेंशियल प्लस काइनेटिक करके 1 केवीटी आ रहा है ना.
यस, ये जो एक है, दिस इज एसेंशियली 1/2 kBt प्लस हाफ kBt प्लस हाफ kBt. This is from the kinetic part of vibration. This is from the potential part of vibration. Make sense?
यस सर.
Lovely. जब तक it makes sense, it's all good. Okay, so this was the diatomic gas when it was hot. What about the triatomic
Can you
atomic
show the
gas?
previous slide?
Huh?
Can you show the previous slide?
Oh, sorry. I'm sorry, I move quickly. I mean, I want to finish all of this. That's the only reason. Sorry. Let me know when you're done.
Done, sir.
Okay, so now the triatomic case. But this time, when all of the three are connected, so an equilateral triangle case. Calculate CP, CV, and gamma. Come on, देखते ही बता दे रहे हैं
सर
CP. Yes.
सर ये कोल्ड कंडीशन पे है ना?
Yes. Yes, this is cold. अगर मैं hot बनाऊंगा तो first of all मैं लिख दूंगा कि hot है, and second of all मैं उसके में वो बनाऊंगा spring.
Yes.
Yes, Harshit, absolutely correct. Okay, so what are the degrees of freedom? Well, you can translate this three directions, so three translations and three rotations. You can rotate it about this axis, you can rotate it about this axis, and you can rotate it about this axis also. So there are six degrees of freedom, and all of these are kinetic energy. There is no potential energy in this. So what's U? 6 into half kBt. U for one molecule. This is 3 kBt. Hence, your CV is du by dt at constant V, which is d by dt of 3 kBt, which is nothing but 3 kb. Okay. Hence, Cp is R plus Cv. So that's 4 kb, 4R, not kb. This is R. All of these are supposed to be R here, on KBT, because here when we're calculating CP and CV, we're not calculating for one molecule, we're calculating for a bunch of molecules. CP and CV are what are called emergent phenomena, as in they're essentially when you have groups of molecules, then only you see a specific heat. It does not make sense to talk about the specific heat of one atom, right? So this is 4R. And what's gamma? Well, that's just 4 by 3. So that's 1.33. Dot, dot, dot. Okay. Any doubts
No,
for
sir.
hot case? Sure. You can do hot case. Uh, सबने करके बैठ गए. Nice. Okay, let's quickly do for hot case. Everybody's an expert at this now. This is lovely. See, because this is this aspect when we're talking about law of equipartition of energy. If you understand this very clearly, then most of thermodynamics should not be a problem for you. Then you will have an intuitive understanding of चीजें क्यों हो रही हैं और कहाँ से आ रही हैं. जो मैं आपने आपको याद है जब हम पहली क्लास में हमने टेम्परेचर के बारे में बात किया था और उसमें हीट के बारे में बात कर रहे थे और थोड़ा सा कंफ्यूजन था. आई थिंक नाउ यू विल अंडरस्टैंड कि वो एनर्जी जो हम बात कर रहे थे वो कहाँ स्टोर हो रही थी और कहाँ से कैसे ट्रांसफर हो रही थी, बिकॉज नाउ वी नो एग्जैक्टली वो कहाँ स्टोर हो रही थी, एंड ऑल ऑफ दैट इज गिवन बाय द लॉ ऑफ इक्विपार्टीशन ऑफ एनर्जी. Lovely. So in this case, what do you have? You have, as per usual, there are six translations, and how many vibrations? There are three vibrations, right? So six translations की वजह से 6 into 1/2 into kBt plus 3 into kBt. So that will give you 3 plus 3, that's 6 kBt. So CV is nothing but 6R and CP is nothing but 7R, and gamma is equal to 7 by 6. Lovely. Beautiful. Now, what about the last case? So, I promise. The linear triatomic. So essentially, it's something like a CO2. Um, you don't need to calculate for the hot case, just calculate for the cold case. That's enough. 9/2, 7/2. Yes, perfect. Perfect. I think everybody knows how to do this. I don't really have to go ahead and do this. If you have any problems, we can talk about this later. So, but this is homework. Take it, consider it as one of your homeworks. For the hot case also. So do both. Okay. So now what about a general polyatomic gas? Polyatomic gas. For a general polyatomic gas, let's say F is the total degrees of freedom. Degree of freedom. So, uh, okay. So, what is the average kinetic energy? Well, that's just 1/2 F times kBT, right? So, let's consider the case where you have no springs, so no vibration modes, or let's say all of them are translation modes. And okay, if you, even if you want to consider vibration modes, you can say that there are V vibration modes, and you can just add V kBt here. But you don't I we don't want to do that. Let's ignore this for some for this case at least. So if you have large number of degrees of freedom, F by 2 kBt, we know that U is
Uh,
nothing. Yes, go ahead.
Sorry to interrupt, but sir, Yashwardhan, he's waiting.
He's waiting where?
Waiting room.
Oh, okay. This guy is super late. इसको क्या समझ आएगा बेचारे को?
नहीं सर, ये एग्जिट हो गया था, अभी था यहाँ
Oh,
पे.
okay, okay. No worries, no worries. Yashwardhan, did you miss something? If you did, we can talk about it.
No, sir.
Lovely, lovely, lovely. ठीक है. So average kinetic energy for a polyatomic gas, F degrees of freedom, vibration को we are ignoring right now. That's just F by 2 kBT. So U is your total internal energy for, let's say, 1 mole of gas. That will be just F by 2 RT. So hence your CV is nothing but F by 2 R, and your CP is what, 1, sorry, R plus F by 2 R, which is 1 plus F by 2 multiplied by R, and hence your gamma is CP by CV, so 1 plus F by 2 divided by F by 2, which is nothing but 2 by F plus 1. Make sense? Yes, no,
Yes,
maybe.
sir.
Yes, sir.
All of
Yes,
this
sir.
makes sense, right? बढ़िया. इस पे मैं बहुत सारे आपको प्रॉब्लम्स असाइनमेंट में दे दूंगा. Okay, I'm removing this, clearing this. Let's move on to calculating more specific heats for slightly different things now. Okay, let's try to figure out, can we from what all information जो अभी तक हमको पता है, can we figure out the specific heat of a solid, like a solid in general. Let's think about a solid in general. So what is the solid, what does a solid look like? Well, a solid looks like a bunch of well arranged atoms. All of these are arranged and they are set, they're bound, as in ये से connected है, ये से connected है, ये सब connected है, ये ऊपर वाला connected है. बे यार तुम नीचे क्यों आ रहे हो? ये ऊपर से connected है, सारे connected हैं, ये से connected, ये से connected है, ये से connected, सब एक दूसरे से connected है, and they cannot move. So they have no translation and no rotation, right? But all they have is vibration, correct?
Yes, sir.
Yes, no,
Yes, sir.
maybe. Huh?
Yes, sir. Yes, sir.
Yes, sir.
Lovely. So each of the atom inside this has how many ways in which it can distribute its kinetic energy, how many degrees of freedom. So it can vibrate along the x-axis, it can vibrate along the y-axis, and it can vibrate along the z-axis. So in the case of a solid, for if we just want to take kinetic energy, then that's three of them. And vibration also, it can vibrate in the x-axis, along the x-axis, or it can vibrate along the y-axis, it can vibrate along the z-axis, correct? So potential energy ke liye bhi there are three. So, what is the total, the average
सर
vibration? हाँ.
हमें वाइब्रेशन के लिए एक्स वाई जेड एक्सेस में अलग अलग क्यों देख रहे हैं? बिफोर दिस आल्सो मतलब हमने सिंपल वाइब्रेशन कंसीडर किया था ना. वी डिडंट
But
टेक.
but that vibration, no, no, wait. What was happening there? There you had one molecule which was connected by one atom, and both of them could move. Here, what is happening is that this molecule इन दोनों से connected है, ऊपर नीचे भी connected है, और आगे पीछे भी connected है by springs, right?
यस सर.
So it can vibrate in the x-axis, it can vibrate in the y-axis, and it can vibrate in the z-axis. Make sense?
यस सर.
Yes, because there are more number of springs that are attached. Essentially, that is why this is happening. So, what is the total average vibrational energy per atom? Well, इसका 3/2 half kbt, and इसका 3/2 sorry 3 into half kbt. So that's essentially 3/2 kbt plus 3/2 kbt, which is 3 kbt. So this implies what is your U? Well, that's nothing but a number of atoms. So if you're taking 1 mole of this thing, so 3 into Na multiplied by Kb into T. This is nothing but R. So this is just 3RT, and hence, but okay. So this is this change in internal energy. What is CV? CV is dq by dv, right? At constant v. dq by dt, whatever I've written. This is just equal to du by dt at constant v plus dw by dt at constant v. But my work done is pdv, and since it's like a solid, you cannot really change the volume. As in, you'll require a lot of energy in order to change the volume. So this term can be treated as zero. So your dq by dt is nothing but du by dt, which is nothing but 3r. So your CV you get as 3r. And hence you can go ahead and calculate CP, and you can go ahead and calculate gamma. This fact that your specific heat for a solid is equal to 3r is given by the name DeLong and Petit's law. This is not a very famous, but yeah, but a relatively famous law in thermodynamics. And now we know where this law essentially comes from. It comes from the fact that the atoms that are arranged, they're stuck there and they can only vibrate. And so the total number of degrees of freedom is just three, and all of those are all the three degrees of freedom are vibrational degrees of freedom, and hence they have both kinetic energy and potential energy parts, and so hence the total energy per molecule is just 3 by 2 kBt, and hence the CV is 3R. This is known as DeLong and Petit's law. But you might be interested in asking the question, what does what actually happens if we actually go ahead and measure, let's say, the specific heat, but take you to a lab and we measure the specific heat of a solid. How does that look like? And actually that looks very, very interesting. I'll just show it to you. I'm plotting it now. Yes. So if you want to plot, uh, if you want to plot CV along the y-axis, along with the temperature, as you increase the temperature, how does CV change? Well, what you see for a solid is that it starts from zero. It goes up, it goes up, it goes up, it goes up, and then it it asymptotically reaches this line. What is this line? This line is 3R line. And the temperature where it reaches is known as the Debye temperature. These terms are important. आपसे कभी वो एग्जाम में पूछ सकता है कि what is Debye temperature. So now you know what Debye temperature is. Debye temperature is a temperature जब एक solid का specific heat reaches an equilibrium point, which after which temperature reaches a constant, which is essentially 3R. Okay. Can you tell me why does this nature, this essentially decrease to zero? Why is that happening as you decrease temperature? कोई बता सकता है?
सर क्वेश्चन क्या है?
Question ये है कि why is CV going to zero? You're essentially from this graph, what you're seeing is that CV जो है तुम्हारा specific heat जो है, it is going towards zero for a solid when your temperature is going to zero. Why is that happening?
Kinetic energy becomes zero.
Well, one way to think about it is if the temperature is zero, your average kinetic energy is zero, and hence there's just no energy stored, and hence your CV is zero. However, that turns out to not be a good explanation, because the actual explanation comes from quantum mechanics. When you're cooling the temperature down so much, quantum effects become very, very significant, and hence this essential behavior of how it decreases to zero, you can calculate all of this. If any one of you go ahead and do a course on physics in the future, and you study and you get to study solid state matter, then you'll do this calculation of how this exact graph looks like. But right now it's something very, very beyond. Lovely. Let's move on from the Dulong and Petit's law to
Can
the
you
specific.
re-explain,
Huh?
please can you re-explain that 3 hour और temperature में जो graph बनाया था आपने?
The this thing, the graph.
Yes sir, yes sir.
So this is what we see experimentally.
Okay.
This is what is happening experimentally. ये तो हमने theoretically सब कुछ drive किया है. When you go ahead and actually do the experiment, what you see is that the specific heat जो है वो एक temperature के बाद ही ये वो constant हो जाती है. But उस temperature से पहले it is not a constant. It actually changes. It goes from zero up to that point. And that temperature जब वो shift होता है, so D by temperature कहते हैं. That's it. Make sense?
Yes sir.
Lovely. Let's move ahead. यार तुम लोग एक और क्लास करवाओगे इस टॉपिक पे, कोई बात नहीं, चलो. Specific heat of water. Let's try to calculate the specific heat of water. What is a water molecule look like? Well, we've already talked about a water molecule. It's H2O. So you have an oxygen here, you have a hydrogen here, and you have a hydrogen here. Okay, so this looks like a decent arrangement. But however, since it's in a fluid form, yes, the molecules will be going around, but the rate at which the molecules are moving will be actually really, really slow. With respect to a gas, obviously, it will be very, 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 very slow with respect to a gas, and actually so slow that you can assume that these molecules are actually static, in the sense that when you are calculating the average vibrational energy, you can take the result from your solids case, which was essentially 3 kBt, the average energy, if you want to calculate, it was 3 kBt, but you have three different atoms here, so it will be 3 kBt multiplied by 3, so this is 9 kBt, and hence your CV turns out to be 9R. It's a del Q by del T, so it's 9R. And this is the reason why water is used as a coolant, because its specific heat is very, very high. This is the highest specific heat that you will see amongst most of the common material that you'll see around yourself. There are extreme materials obviously you can make in order which have higher specific heat, but the common most material, it's water. And what does having a higher specific heat means? It means that it can absorb a lot of heat without really increasing its temperature a lot. So that means you can use it as a coolant. आप उसको चीजों को ठंडा करने के लिए यूज कर सकते हो, because it's absorbing a lot more heat than any other thing you would use. Okay. Lovely.
Sir.
हाँ, go
सर
ahead.
आपने स्टार्टिंग में क्या बोला था कि फ्लूइड बहुत you said something in the start.
Yes. So essentially, by when doing this small derivation, what we are assuming is that the molecules are not really moving a lot. It's essentially like the solid, but the difference is that उसमें एक molecule उसके molecule में खाली एक ही चीज था, एक ही atom था. इसमें हर एक molecule में 3 atoms हैं. So that's why you just multiplying it by 3.
So why do we multiply by 3?
Because there are 3 atoms here, right? See, if you see the structure of water, if you actually, okay, fine, let's go into a slight bit of detail here, because it's important. Let's say you have oxygen here, you have hydrogen here, and you have hydrogen here. Now, what is the charge on this hydrogen? So let's say because of which it became this bonded. Well, it was an H plus, right? Or was it H minus? What was it? Oxygen is O2 minus
Yeah, yeah, H plus.
H plus. Yes, this was H plus, this was H plus, this was 2 minus. Now, there is another molecule of water उसकी side में. This hydrogen will also be attracted towards this oxygen, right? This is what is we call as hydrogen bonding.
Yes, sir.
Because of this hydrogen bonding, what essentially happens is that the structure जो होता है वो fix हो जाता है. इस water का जो structure है वो fix हो जाता है. And hence it's very similar to the problem we solved for the solid. But अब हर इसमें क्या हो रहा है कि हर एक ये जो हाइड्रोजन है ये किसी और ऑक्सीजन से जाके जुड़ा होगा through hydrogen bonding. This hydrogen is attached to some other oxygen through hydrogen bonding. This hydrogen is attached to some other hydrogen. This oxygen is attached to some other hydrogen. So all of these are attached to each other, either via strong bonding or via hydrogen bonding. That's why you can consider this as like a solid structure, like a lattice. And then for a lattice we already calculated कि हमारा कितना आना चाहिए, हमारा आना चाहिए 3 kBt. And since all of these three atoms are behaving like centers in the lattice, so you are multiplying it by 3. Does that make sense?
Yes, sir.
Lovely. Lovely, lovely, lovely. It's nice. थोड़ा सा डिटेल में घुस की चीजें ज्यादा अच्छे से समझ आती हैं. That is lovely. We have 10 minutes, 9 minutes. Okay. Um, okay. Let's move ahead. Jaldi se. Let's finish this chapter quickly. Next class may we'll only do problems. Let's finish this. Okay. Let's talk about mean free path. Now, how do you define mean free path? Well, what essentially you're saying is that you have a container, big ass container, जिसमें एक let's say you're tracking this particular molecule. ये molecule को आप track कर रहे हो. ये molecule गया यहाँ से यहाँ तक, यहाँ पे टकराया, उसके बाद यहाँ से यहाँ तक गया, यहाँ पे टकराया, उसके बाद यहाँ से यहाँ तक गया, फिर टकराया, फिर वापस गया, यहाँ यहाँ तक गया, फिर यहाँ पे टकराया, फिर यूं गया, फिर यूं गया, फिर यूं गया, फिर यूं गया. मतलब going in a random motion. This is what essentially we call Brownian motion. What the mean free path defines is essentially, it's first of all, it's given by lambda average, sometimes written as lambda bar. It's essentially the same thing. This mean free path is essentially telling you the average distance each molecule has to travel before it comes into a collision. Okay, so what is the mean free path? It's the average distance. How do I remove this? Wait, I'll write it here. It's the average distance a molecule travels before colliding with another molecule. Okay, सो अगर हमको एवरेज ही निकालना है, सो एवरेज कैसे निकालते हैं? एवरेज विल बी, हम लेट्स से कि पहला जो डिस्टेंस कैलकुलेट चला वो लैम्डा 1 चला, फिर लैम्डा 2 चला, फिर लैम्डा 3 चला, फिर लैम्डा 4 चला, डॉट 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 लैम्डा n n स्टेप्स लिए, स्मॉल n n स्टेप्स लिए, तो लैम्डा n वाज द आखिरी स्टेप. सो व्हाट इज द एवरेज? वेल दैट्स जस्ट लैम्डा 1 प्लस लैम्डा 2 प्लस डॉट 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 लैम्डा n डिवाइड बाय n. मेक सेंस?
Yes, sir.
What are we assuming here? We are assuming two things specifically. First of all, each एक मिनट, I write it in the actually I'll write it here a bit. Okay, what are we assuming here? Each molecule of the gas is a sphere of diameter d. Okay, ये सारे spheres हैं of diameter d, and uh, and let's assume another very very important assumption. It is obviously not valid, but we'll see why this is very useful. All molecules of the gas except for the one under consideration under consideration A. Actually, you know what? Let's just do this next week. Sorry, not next week. In the next class, because इसमें बहुत है आगे और ये अगले 5 मिनट में cover नहीं हो पाएगा. So let's do this. Let's undo this all, and we'll talk about it next week. अभी तक जो हमने किया, उसमें कोई problem?
नो सर, सर इसका सिग्निफिकेंस क्या है?
किसका significance?
मीन फ्री पाथ.
मीन फ्री पाथ का ये हम कल करेंगे. ओके, मीन फ्री पाथ को भूल जाओ. मीन फ्री पाथ का समझो कि अभी हमने बात की नहीं है. विल टॉक अबाउट इट इन द नेक्स्ट क्लास. अभी खाली स्पेसिफिक हीट तक बात करो. वहां पे कोई प्रॉब्लम है?
सर
गो अहेड.
सेड नो सर, नो सर.
Oh no sir. Lovely, lovely, lovely. um okay, so how about this, let's meet tomorrow and let's finish. कल पूरा आपका सिलेबस खत्म हो जाएगा and then we can party. चलो, take care. I'll
थैंक
see
यू
you.
सर.
हाँ, go ahead.
थैंक यू सर.
No problem, no